So what we have seen so far is 2 and 3 valve conduction mode and 3 and 4 valve conduction mode. So for 2 and 3 valve conduction mode, the overlap angle U is greater than 0 and less than 60 degrees. For 3 and 4 valve conduction mode, U is greater than 60 degrees. Now we'll see what happens if U is exactly 60 degrees. So if suppose U is 60 degrees. Now one can see what is the number of valves the number of valves that is conducting at any instant. So if U is less than 60, at any instant either 2 valves conduct or 3 valves conduct. If U is greater than 60, at any instant either 3 valves conduct or 4 valves conduct. When U is exactly 60, then at any instant we have only 3 valves conducting. So what we get for U equal to 60 is 3 valve conduction. So we can try to do the analysis as we did for the previous 2 cases. So in order to do a steady state analysis, we need to just consider only one cycle, in fact only one interval in fact. So we have one cycle of the AC side voltage or current equal to 6 intervals. So the 6 intervals are identical in width. Each interval is of duration 60 degrees. Each of duration 60 degrees. So it's sufficient to consider one interval for the sake of steady state response. So let us consider one interval. So we'll always start with the interval which starts at, we'll always use the interval which starts at alpha. So let us consider the interval alpha less than omega ot less than alpha plus 60 degrees. So in order to do the analysis for this interval, I need to consider the equivalent circuit. So let me show the equivalent circuit which contains only those elements which carry non-zero current. So I have an equivalent circuit with 3 sources, voltage sources, EA, EB, EC. So I have valve 1 in series with EA, valve 3 in series with EB. In series with EC, I have valve 2. The DC side voltage, instantaneous voltage is VD, and the current that is flowing through valve 3 is I3. The current through valve 1 is I1, which is nothing but ID minus I3. So let us try to apply Kirchhoff's voltage law to the loop containing EA, EB, the 2 inductances L, the valves 1 and 3. So by Kirchhoff's voltage law, I get di3 by dt minus L d by dt of id minus I3 is equal to Eb minus Ea. Since id is a constant, the left hand side is 2L di3 by dt is equal to Eb minus Ea. Root 2V sine omega out. So we can solve this equation, and we know the initial condition. So first of all, this equation is applicable for omega ot greater than alpha and less than alpha plus 60 degrees. So we know that I3 at alpha is 0. We get the solution as I3 equal to V by root 2 omega OL into cos alpha minus cos omega ot. So this is the expression for I3 from alpha to alpha plus 60 degrees. At alpha plus 60 degrees, I3 reaches the value ID. So I3 at alpha plus 60 degrees is equal to ID. So if I substitute omega ot equal to alpha plus 60 degrees on the right hand side of the previous equation, and I3 is equal to ID, then I get ID is equal to V by root 2 omega OL into cos alpha minus cos alpha plus 60 degrees. So this V by root 2 omega OL as a notation, which is IS. So we have defined a current IS. So I get ID is equal to IS into cos alpha minus cos alpha plus 60 degrees. Now we got a relationship between ID, IS, alpha, and of course U for the 2 and 3 valve conduction mode, and 3 and 4 valve conduction mode. Now in this case, for 3 valve conduction mode, there is no U, of course. U is exactly equal to 60. So the relation is between ID, IS, and alpha. Now let us say whether these expressions for ID in terms of IS, alpha, and U for the 3 different operating modes are somehow related. So let us take the equations that we already obtained. So for 2 and 3 valve conduction mode, we got an equation relating ID, IS, alpha, and U. So the equation that we got was ID is equal to IS cos alpha minus cos alpha plus U. So since this is applicable for 2 and 3 valve conduction mode, it's as good as saying this is applicable for U greater than 0 and less than 60 degrees. Similarly, we got an equation for 3 and 4 valve conduction. So the equation is ID is equal to IS by root 3 into cos alpha minus 30 degrees minus cos alpha plus U plus 30 degrees. So this is applicable for U greater than 60 degrees and less than 120 degrees. So the equation that we obtained just now, that is ID equal to IS cos alpha minus cos alpha plus 60 degree for the 3 valve conduction mode, is for U equal to 60 degrees. So let us write that also. For 3 valve conduction mode, ID is IS cos alpha minus cos alpha plus 60 degrees. This is for u equal to 60 degrees. Now let me see whether the equation that we obtained for 2 and 3 valve conduction mode is applicable for u equal to 60. So it is to be noted that it's applicable for u less than 60, but is it valid for u equal to 60? It can be shown that it is true. Suppose I take limit of the right hand side in the equation which gives the expression for ID for u less than 60 degrees. So if I take limit of is cos alpha minus cos alpha plus u. So if I take the limit as u tends to 60 degrees. Now it's easy to see that this is equal to is cos alpha minus cos alpha plus 60 degrees. So the equation which is derived for u less than 60 degrees is actually applicable for u equal to 60 degrees also. Similarly, if I take the expression for ID in terms of is alpha and u for u greater than 60 degrees. So that means the limit of is by root 3 cos alpha minus 30 degrees minus cos alpha plus u plus 30 degrees. So if I take the limit of this expression as u tends to 60 degrees. So it is to be noted that this expression is valid for u greater than 60. So we are trying to show that it is valid even if u is equal to 60. So it can be proved that this is also equal to is cos alpha minus cos alpha plus 60 degrees. So this is not as obvious as the previous case, but I would leave it to you to show that this is true. So whatever we got for u less than 60 degrees and u greater than 60 degrees is applicable for u equal to 60. So what one can say is I can have this equation which was earlier valid for u greater than 0 and less than 60 degrees to be true even for u equal to 60 degrees. That means this is valid for u greater than 0 and less than or equal to 60 degrees. So please note there is a difference between this equation 1, let me call this equation 1, this is equation 2, and say this is equation 3 and this is equation 4, 5 and 6. So 1 and 6, equations 1 and 6 are almost same, but actually 6 has something more. It also has 3. So that's because u is not just less than 60, it's less than or equal to 60. Similarly, from equation 2, what I have is ID is equal to is by root 3 cos alpha minus 30 degrees minus cos alpha plus u plus 30 degrees. So from equation 2, this is applicable if u is greater than 60 degrees and less than 120 degrees. But we just now showed that it is also applicable if u is equal to 60 degrees. So let me call this as equation 7. So equation 7 is nothing but equation 2 with an additional information that it's valid even for u is equal to 60 degrees. Now let us move on to the DC side voltage. So if I take the same interval alpha less than omega ot less than alpha plus 60 degrees. So we got an equation by applying Kirchhoff's voltage law. So from the same circuit diagram, so if I look at the circuit diagram, so I can get an expression for VD in terms of EB, EC and the drop across the inductance in series with the voltage source EB. Of course, the valves 2 and 3 act as short circuit, and the inductance in series with valve 2 is acting as a short circuit because the current through this inductance is ID, which is constant. So I can get an expression for Vd from this circuit. So Vd can be written as Eb minus L di3 by dt minus Ec. So that should be obvious from this circuit. So Vd is Eb minus L di3 by dt minus Ec. And we also got an expression for L di3 by dt. So L di3 by dt is Eb minus Eb. So I'll just substitute this expression for L di3 by dt, which is Eb minus Ea, in this equation. So it is Eb minus it's in fact Eb minus Ea is 2L di3 by dt. So it is Eb minus Ea by 2 minus Ec. So this can be simplified. Eb minus Eb by 2 is Eb by 2. So I have Eb by 2 plus Ea by 2 minus Ec. And Ea plus Eb plus Ec is 0. So Ea plus Eb is minus Ec. So we get finally Vd equal to minus 3 by 2 Ec. So if I look at the average value of the DC side voltage, so let me use the same notation which we have been using. So we'll use uppercase V with a subscript D. So I have to take the average value. So I get the average value by taking the integration over one interval. So this is 3 by pi integral Vd d omega ot. So if I take the interval alpha to alpha plus 60 degrees, then I know the expression for Vd. So just now I got the expression for Vd for alpha to alpha plus 60 degrees. So it is minus 3 by 2 is so this is 3 by pi alpha to alpha plus 60 degrees minus 3 by 2. Ec is root 2 by 3 V sine omega ot minus 90 degrees. So if I evaluate this integral, so I get an expression for Vd. So I'll leave it to you to derive that Vd is equal to Vdo by 2 into cos alpha plus cos alpha plus 60 degrees. So VDO is having the same meaning that was used for 2 and 3 valve conduction mode and 3 and 4 valve conduction. So this is the expression for Vd. So we have an expression for Vd in terms of VDO and alpha. So if you recall, we had expressions for Vd in terms of VDO, alpha and U for the 2 and 3 valve conduction mode and 3 and 4 valve conduction. So let us look at what was the expression for 2 and 3 valve conduction mode and 3 and 4 valve conduction. So for 2 and 3 valve conduction mode, the equation relating Vd, VDO, alpha and U is VDO by 2, Vd equal to VDO by 2 cos alpha plus cos alpha plus C. So this equation is valid for U greater than 0 and less than 60 degrees. We also got an equation relating Vd, VDO, alpha and U for 3 and 4 valve conduction. So for 3 and 4 valve conduction mode, the equation that we derived is Vd is equal to root 3 VDO by 2 cos alpha minus 30 degrees plus cos alpha plus u plus 30 degrees. So this equation is valid for u greater than 60 degrees and less than 120 degrees. And just now we derived for the 3-valve conduction mode. So for 3-valve conduction mode, we got Vd equal to VDO by 2 cos alpha plus cos alpha plus 60 degrees. So this is applicable for u equal to 60 degrees. So let me call this as equation 1 now. This is equation 2 and this is equation 3. Now the idea is to show that I can just use equations 1 and 2. I mean, essentially showing that equations 1 and 2 are valid for u equal to 60. So this is similar to what we did for the equation relating IDIS alpha and u. So instead of having 3 different equations, one for u less than 60 degrees, one for u greater than 60 degrees, and one for u equal to 60 degrees, we have this equation 6 and 7, which includes the value of u equal to 60 degrees. So we are going to do a similar thing even for Vd. So if I look at the expression for Vd for u equal to 60 degrees, of course it is in terms of VDO and alpha, there is because u takes a specific value of 60 degrees. So what I do is I will just try to take the limit of the expression for Vd in equation 1 as u tends to 60 degrees and show that we get the equation 3. So what I am trying to do is I will take equation 1. So the right hand side of equation 1 is VDO by 2 cos alpha plus u. So if I take the limit of this as u tends to 60 degrees, so what I get is VDO by 2 into cos alpha plus 60 degrees. So which is nothing but the expression for Vd for u equal to 60 degrees. Similarly, if I take the limit of the expression for Vd, which is appearing on the right hand side of equation 2, that is limit of root 3 VDO by 2 into cos alpha minus 30 degrees plus cos alpha plus u plus 30 degrees. So this can be shown to be equal to VDO by 2 cos alpha plus 60 degrees. It is not as obvious as the previous case, but it's not difficult to derive. So I will leave it to you to show that this equation is true. So I get this as equation 4 and 5. So what one can do is instead of using equations 1, 2, 3, I can just use 2 equations. So I can say that Vd is equal to VDO by 2 cos alpha plus cos alpha plus u. So instead of saying that this is valid for u greater than 0 and less than 60 degrees, I will say this is also valid for u equal to 60 degrees. So let me call this equation 6. Similarly, if I take the expression for Vd in terms of VDO, alpha and u for 3 and 4 valve conduction mode, then it is Vd equal to root 3 VDO by 2 cos alpha minus 30 degrees plus cos alpha plus u plus 30 degrees. So this equation is valid for not just u greater than 60 degree and less than 120 degree, but also for u equal to 60 degrees. So essentially it says that 6 and 7 can be used instead of 1, 2 and 3. This is the same as what we did for the equation relating IDAS alpha. 6 and 7 can be used instead of 1, 2 and 3. Now, as in the case of 2 and 3 valve conduction mode or 3 and 4 valve conduction mode, let us form a table where we show all the intervals, the valves that conduct, the expression for the instantaneous DC side voltage, the voltage across the valve, and also try to find the jumps in the voltage across the valve. So let us take all the 6 intervals. Omega OT greater than alpha and less than alpha plus 60 degrees. Then alpha plus 60 degrees less than omega OT less than alpha plus 120 degrees. Alpha plus 120 degrees less than omega OT less than alpha plus 180 degrees. And so on. So these are the 6 intervals in one cycle. So let me see what are the valves that conduct in each of these intervals. Valves that conduct. So in the first interval, that is from alpha to alpha plus 60 degrees. So valve 3 is turned on at alpha. 1 and 2 are already conducting, they continue to conduct. So valves that conduct in the first interval are 1, 2 and 3. In the second interval, 2, 3, 4. So in the second interval, actually 1 has stopped conducting and 4 has started conducting. Then 3, 4, 5. 4, 5, 6. 5, 6, 7. Sorry. 5, 6, 1. 6, 1. Then the cycle repeats. Then if I want the instantaneous DC side voltage V, we already know what is the expression for VD in the first interval, we just derived. But we also know what is the expression for VD when we know what are the valves that conduct from the previous 2 tables, that is for the table for 2 and 3 valve conduction mode or the table for 3 and 4 valve conduction mode. So this is something which we already know, so we can straight away write this. So this is minus 3 by 2 EC. This is 3 by 2 EB minus 3 by 2 EA, 3 by 2 EC minus 3 by 2 EB, 3 by 2 E. Then voltage across one of the valves, say valve 1. Of course, we have also seen the expression for voltage across valve 1 when we know what are the valves that conduct. So a few of the entries in this column are easy. When valve 1 is conducting, actually voltage across valve 1 is 0. So in the first interval, valve 1 is conducting, so it is 0. In the last 2 intervals, valve 1 is conducting, so voltage across valve 1 is 0. Now, of course, we got the expressions for the other 3 intervals also, but one point to, of course, note again is that when valve 4 is conducting, then voltage across valve 1 is minus V. So in all the 3 remaining intervals, valve 4 is conducting. So the voltage across valve 1 is minus Vd. So it is minus 3 by 2 Eb in the second interval, 3 by 2 Ea in the third interval, and minus 3 by 2 Ec in the fourth interval. So these are the expressions for voltage across valve 1. We can also get the expression for the magnitude of the voltage jumps. So jumps in voltage across valve. So this is an information which is required for knowing the dV by dt stress. So you see that there are 4 jumps. There is a jump from 0 to minus 3 by 2 Eb, minus 3 by 2 Eb to 3 by 2 Ea, 3 by 2 Ea to minus 3 by 2 Ec, and minus 3 by 2 Ec to 0. So if I want to know the 4 jumps, so what I need to do is take the difference in these 2 expressions and evaluate it at the corresponding instant. So the first jump is minus 3 by 2 Eb minus 0, evaluated at alpha plus 60 degrees. Similarly, the second jump is 3 by 2 Ea plus 3 by 2 Eb, evaluated at alpha plus 120 degrees, and so on. So I'll leave it to you to verify that these jumps are given. Right? The first jump is minus square root of 3 by 2 V cos alpha. The second jump is minus square root of 3 by 2 V sin alpha plus 30 degrees. The next jump is minus root 3 by 2 V sin alpha plus 30 degrees. And the last jump is minus root 3 by 2 V sin alpha minus 30 degrees. So that is about the 3-valve conduction mode. So for the sake of completeness, we have also considered the 3-valve conduction mode in addition to the fluent 3-valve conduction mode, which is the normal operation, and 3 and 4-valve.